I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
In our data-driven world, the demand for faster, more secure, and energy-efficient technologies is reaching new heights. And at the center of this race lies the technology that could redefine how we compute and communicate: silicon photonics. At its core, silicon photonics merges two great forces: photonics, the science of light, and silicon-based electronics, the foundation of every digital chip we use today. Traditional electronics rely on electrons traveling through copper wires, but electrons have their limits. They create heat, they face resistance, and they simply can't move fast enough to keep up with our exponential data demands. Photons, on the other hand, move at the speed of light. They don't generate heat or electrical noise, and they can carry vast amounts of data through tiny optical channels. Silicon photonics takes advantage of this by etching microscopic structures, waveguides, modulators, and detectors directly onto silicon chips. These structures guide and control light with extreme precision, enabling blazing fast communication and ultra-efficient data transfer. Today, this technology already powers the invisible arteries of the internet, from data centers to undersea cables. But that's just the beginning. The real revolution begins when silicon photonics meets quantum technology. Quantum physics works in a strange but powerful way. Particles like photons can exist in multiple states at once, a principle called superposition. And when two particles become entangled, they share information instantly, no matter how far apart they are. These are the building blocks of quantum computing and quantum communication, fields that promise to break today's computational limits and redefine cybersecurity itself. Silicon photonics turns out to be a perfect partner for this quantum world. Photons are naturally resilient. They're not easily disturbed by electromagnetic interference. And silicon, being the cornerstone of modern microchip manufacturing, provides a scalable and cost-effective platform. That means the same factories producing your smartphone chips could one day be mass-producing quantum processors. In a quantum computer, information isn't stored as simple bits of zeros and ones, but as qubits, quantum bits that can be both at once. By encoding these qubits in photons and processing them on silicon chips, researchers can build powerful quantum processors capable of solving problems that would take classical supercomputers millennia. Startups like PsiQuantum and Xanadu, alongside tech giants and university labs, are using silicon photonics to design scalable quantum architectures. They're exploiting the natural advantages of light, coherence, speed, and parallelism to build processors that could revolutionize drug discovery, logistics optimization, and even climate modeling. These same silicon photonic devices are also forming the backbone of quantum key distribution, or KQD, a communication system so secure that even if someone tries to intercept your data, physics itself reveals the intrusion. Projects like China's Micius satellite, Europe's quantum communication infrastructure, and North America's quantum testbeds are already proving the concept, using silicon photonic chips to link quantum nodes across cities, countries, and even space. This is the foundation of what scientists call the quantum internet, a future network where information travels as entangled light, making data breaches and cyber attacks virtually impossible. And we're getting closer to that reality faster than many expected. A recent breakthrough from researchers at STMicroelectronics, Télécom Paris, and CTN in France shows how rapidly this technology is evolving. They developed ultra-compact silicon ring resonators, tiny circular waveguides that can generate more than 70 distinct light frequencies within an area smaller than a grain of sand. Using a technique called spontaneous four-wave mixing, they created pairs of entangled photons, the building blocks of quantum communication, and controlled 34 single qubit gates simultaneously. That's real quantum processing power, right on a chip. Proof that the vision of a scalable quantum network is moving from theory to hardware. What makes this breakthrough so significant is scalability. These resonators are fabricated using industry-standard semiconductor techniques, meaning they can be produced on the same lines that already make billions of microchips. The result is miniature quantum systems that are compact, reliable, and ready for real-world deployment. The potential goes far beyond computing. In secure communications, integrated quantum photonic chips could protect financial transactions, government data, and defense systems with unbreakable encryption. In healthcare, quantum-powered photonic sensors could detect diseases long before symptoms appear. In navigation, quantum-enhanced gyroscopes could outperform GPS deep underwater or in space. And in environmental monitoring, photonic sensors could detect the faintest traces of pollutants or seismic changes with incredible accuracy. Together, silicon photonics and quantum technology are setting the stage for a new era, one where light doesn't just carry our data, but computes it, protects it, and even senses the world around us. The convergence of these fields could transform entire industries, from finance and medicine to defense and artificial intelligence. The quantum leap is coming, and thanks to silicon photonics, it's coming on a chip.
Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.